Hey guys, here are your notes on section 4.4, day 1. Excuse me. In section 4.4, you're going to be asked to find the complex zeros. So in section 4.3, it was all about finding just the real zeros. If we ended up with any imaginary zeros, we didn't count them as answers. We just found real zeros. So now in this section, we're going to be finding all possible zeros, whether they be real or imaginary. But I just want you guys to understand something, because I feel like sometimes the way they say find complex zeros, it confuses students. I don't want you guys to think finding complex zeros means that you're just finding the imaginary ones. No, if you see the word complex numbers, I need you guys to understand that to find a complex zero, it means to find all zeros possible, whether they be real or imaginary, okay? Don't just think that complex means to find the imaginary ones, because I want you guys to remember that technically our number system is a complex number system, okay? And it's made up of numbers of this form, a plus bi, right? This is the standard form of a complex number. And then they branch out into two subcategories, if you will, all right? If the b value is equal to 0, well, 0 times I would be 0. So then you would just have a. A is the pure real number part of the complex number. So if b is equal to 0, then this complex number becomes a pure real number. And then real numbers branch out into two subcategories. If it can be written as a fraction, it's a rational number. If it can't be written as a fraction, then it's what we call an irrational number, right? Rational numbers were basically any number that can be or already is written as a fraction. So you could think of 8, you could think of negative 37, you could think of 2/3, you could think of negative 4.625. All of those are rational numbers. They are numbers that can be or already are written as a fraction, all right? But if you're not going to be able to be written as a fraction, then you break into a group called an irrational number. And irrational numbers are numbers that are non-repeating, non-terminating decimals. They're extremely ugly, hard numbers to work with. So pi used to be the most famous irrational number. Then you guys learned about the number e in Algebra 2 last year when you got to exponentials and logarithms, all right? And then you have, just like your irrational numbers, is the square root of any prime number, like the square root of 2 or the square root of 11. Those are some popular irrational numbers as well, all right? So if you are asked, is this a complex number? Yeah, these are complex numbers. They are coming from a complex number system. So I don't want you to associate the word complex with imaginaries. A complex number can be a real number, or it can be imaginary. So to be an imaginary number, it just means that the b value does not equal 0. So then you have a real part and an imaginary part, and it still makes that number imaginary, all right? Then the imaginary numbers break off into two subcategories. If the a value is equal to 0, then it's what we call a pure imaginary number. It's bi, right? There's no real part to it. It's just like 3i or negative 15i. Those are pure imaginary numbers. They have no real part to that complex number. All right, but if a does not equal 0, then you become what we call a complex number in the form a plus bi, like 3 plus 2i, or negative 4 plus 20i, and so on. Those are an imaginary number, also what we call complex. So I know it can be confusing if this is what we call a complex number, but so are these, because our number system is a complex number system that branches out into two subcategories, real or imaginary. So I apologize for that long-winded spiel, but I just want you guys to realize that when you are asked to find a complex zero, that can mean a real zero or an imaginary zero. Because I think your homework starts saying things like find the real or complex zeros. And that is technically, if you ask me, that's wrong. They should not have to put the word real zeros in there if they've already asked you to find the complex ones, because by asking us to find a complex zero, that counts as real or imaginary numbers, okay? So just remember that. Finding complex zeros means that we are finding all possible real or imaginary zeros, okay? All right, so in this section today, we're going to kind of go over just a few theorems. Again, because these polynomials are going to get a higher degree and their zeros are going to be harder and harder to find, the more proofs and theorems that we have that help us establish what the zeros could be, the better it is for us, because these polynomials just get harder and harder to work with, okay? So we just have a bunch of theorems that we have to go over, and then a few examples. All right, so number one, extremely important theorem that you guys never want to forget, we've already talked about it, is the fundamental theorem of algebra. And that theorem says that a polynomial of degree n has at most n zeros, right? Whether they be real or imaginary. So basically, guys, it's saying if you are a degree 5 polynomial, then guess what? A degree 5 polynomial is going to have at most 5 zeros. And the only reason we say at most is, trust me, it's going to have exactly 5 zeros. But if two of them repeat, like x equals 2 and x equals 2, so some people might think, oh, well, it really only has 4. But that's not the case. If you count x equals 2 and x equals 2 as two separate zeros, even though it's a repeated one, you will definitely end up with 5 total zeros. All right. So just know that whatever the degree is, that's exactly how many zeros that polynomial can have. Okay. All right. Another theorem, it doesn't get a name. Another theorem says every complex polynomial f of x of degree n that is greater than or equal to 1, so a linear polynomial or greater, it has to have at least one complex zero. So basically, if you are a degree 1 polynomial, then you're going to have 1 0. So every polynomial of a degree n of being 1 or higher, it's going to have at least one complex zero. A degree 2 will have 2 complex zeros. Degree 3 will have 3 complex zeros, right? Whether they be real or imaginary, it doesn't matter. It will have 3 when you total them all up at the end. All right. So again, every polynomial function has at least one number, whether that number be real or imaginary, that will make the function equal 0, right? That's what it means to be the 0. You are the number that when you plug it in, it makes the 0 come out of that equation. So again, every single polynomial of degree 1 or higher is going to have at least 1 0, one number that will make it equal 0. Okay? All right. So now, according to the fundamental theorem of algebra and the factor theorem, this is another theorem we can come up with, okay? This theorem, again, does not have a name. It's just something that we're going to be able to use. And again, it kind of goes off of this one, the fundamental theorem of algebra, and what the factor theorem is saying. All right, it says every complex polynomial function f of x of degree n greater than or equal to 1, so a degree 1 polynomial or higher, it can be factored into n linear factors, not necessarily distinct, and we'll talk about that, of the form this. So guys, basically it's saying that if you have a degree 5 polynomial, it's going to have exactly 5 zeros, and then each one of those zeros can be written as a linear factor, okay? Where a sub n, r sub 1, r sub 2, r sub n, again, it doesn't really matter, are complex numbers. That is, every complex polynomial function of degree n greater than or equal to 1 has exactly n complex zeros, some of which may repeat. That just means, like I said, some of those zeros might be repeated. It might have a multiplicity of 2 or a multiplicity of 3, but that's fine. But they each count as one of those total 5 zeros to that degree 5 polynomial. All right, so again, this theorem is saying that once you know a zero, however weird that zero is written, whether it's real number or an imaginary number, that zero can be turned into a linear factor. So guys, what this theorem is saying is if you know 4 is a zero of that polynomial, then you know you could write x minus 4 as one of its linear degree 1 factors of the original polynomial you were working with. If negative 1 was a zero of that polynomial, then he could be written as a factor x plus 1/2. That's a linear factor of that polynomial. Every single zero that goes with this polynomial can be written as a linear factor. That's kind of what we were doing in the homework in the end of 4.3 when they were asking you to find the zeros and then write it in factored form. You took all those zeros as no matter how weird they looked and you wrote them as those linear factors, right? Okay. And then if plus or minus root 3 were zeros, then you could write each individual one of those zeros as a zero, as a factor, as a linear factor. You could say if it was positive root 3, you could say x minus root 3 is a linear factor of that polynomial. All right, if negative root 3 was a zero, then you could say x plus root 3 is one of its linear factors, that polynomial, okay? So again, what's going to happen is once we start knowing and finding out zeros, or if they're going to give us information that what are the zeros are, we could potentially create that polynomial function that has those zeros. Now, the reason they say maybe not distinct is that goes back to who that leading coefficient would have to be. Remember when we were writing polynomial functions and we said, well, if they're not going to give us more information to go off of other than the zeros, then we could let a be 1, right? So again, that just means that if we know the zeros, we could technically come up with a non-distinct equation just by using all of those linear factors. And then you'd still have a polynomial function that definitely has these as its zeros, okay? All right, perfect. All right, so then let's go down to another theorem that's going to help us kind of establish what the zeros of a polynomial function have to be. All right, this is called the conjugate pairs theorem. And what the conjugate pairs theorems is, if you remember when we were like rationalizing denominators, sometimes, you know, if the denominator was 1 over, let's say, 3 plus root 2, we would have to use the conjugate 3 minus root 2 in order to get the denominator to be rationalized. And we times top and bottom by 3 minus root 2, right? The denominator's conjugate. Because when you multiply conjugates, it makes all of that bad stuff disappear from the problem, okay? So a conjugate pairs theorem, it says, let f of x be a polynomial function whose coefficients are real numbers if r equals a plus bi. So if one of its zeros is r, which is a plus bi, if that's a zero of the polynomial f, then the complex conjugate, r conjugate, that bar just means it's the conjugate, equals a minus bi is also a zero. So guys, it's basically telling you that if a plus bi is a zero, then his conjugate, a minus bi, must also be a zero. And that kind of makes sense. They have to come in pairs. If you're going to have some imaginary, because that's an imaginary number, it's got an I in it. If you're going to have an imaginary zeros have to come in pairs. Guys, look at this problem. What if I asked you to solve this? X minus 2, the quantity squared, plus 25 equals 0, right? If I solve this, I would minus 25. I would square root both sides. I would get the square and radical cancel out. So I would get x minus 2 equals plus or minus, right? Taking the square root of a square creates two versions of this. Plus or minus the square root of negative 25 is 5i. So you get plus or minus 5i. When you take the square root of a negative, that's how I comes out to play. So when you're square rooting both sides of an equation, you're creating two possible versions of that imaginary number, the plus or minus. So to get an imaginary number, you must have taken the square root of something negative, and taking that square root is going to cause a plus or minus to come into play. So you're going to be creating two possible roots by using that square root. So the conjugates, they have to come in pairs because you are getting a imaginary by square rooting something, and your square rooting is going to create this plus or minus version of that answer. So now when I finish solving for x, I add 2 over and I get x equals 2 plus or minus 5i. So I got 2 plus 5i as one of its zeros, and then I got 2 minus 5i as one of its zeros. They're going to come in pairs when you get an imaginary zero, all right? Because you're going to have that square root that creates that plus or minus. All right, so that's what it's saying. They're saying that if you know a plus bi is a root, you don't even have to be told this. It is assumed that a minus bi is then also a zero of that polynomial function. All right, so like it says, if 2 plus 5i is a zero of a polynomial, then you automatically know his conjugate, 2 minus 5i, is also a zero. If you know that negative 2i is a zero, this imaginary zero has to come in a pair. It has to come with its conjugate. So the conjugate to negative 2i is positive 2i. All right, so when they start listing out what the zeros to a potential polynomial function are, they don't technically have to list all of them for us to know what all of the possible ones could be. We know that the complex ones, the imaginary ones, they are going to come in pairs. All right, perfect. Where's the other sheet? Okay. All right, another theorem. So this is kind of like it's not actually a theorem, it's a corollary from the last theorem. If we know the conjugate, the complex conjugates are going to come in pairs, then a corollary is a polynomial function of odd degree with real coefficients. It has to have at least one real zero. They can't all be imaginary. If you are an odd degree polynomial function, you have to have at least one real zero. Now, an even degree polynomial does not have to have at least one real zero. An even degree polynomial can have every single x-intercept or zero be imaginary. It does not have to be anything real when you're solving an even degree polynomial. They can all be imaginary. But an odd degree one has to have at least one real zero. And the reason is this. Let's say you have a degree 3 polynomial. Then we know it has to have 1, 2, 3 zeros. It has to have 3 zeros if it's a degree 3 polynomial, right? Okay. Well, if let's say the first one ended up being an imaginary 0, right? Well, an imaginary 0 has to come in a pair. So that means that this 0, the second 0, must have been his conjugate. So you know they come in pairs, so you know this one also had to be imaginary, which means could the third possible 0 be imaginary as well? No, because if the third 0 was imaginary, then his conjugate would have to be a 0 as well, and now you'd have 4 zeros to a degree 3 polynomial, and you never have more zeros than the degree. So that means that with an odd degree polynomial, you're always going to have this odd man out at the end that can't have a pair. It's got to be a real 0 because only a real 0 can come as a single. It does not have to have a matching pair if you are a real 0. So all of your odd degree polynomials can have, an imaginary and its pair, but there's always going to be that last one, that odd man out that has to be real. Okay? All right, look, same thing here. If you had a degree 5 polynomial, all right, well then it has to have 5 zeros. If this one was imaginary, well then this one would have to be his conjugate. They have to come in pairs. If this one was imaginary, then the fourth one would have to be his pair, right? But the fifth one can't be imaginary because then he would have to have a pair and I'd need 6 zeros. So again, this would have to be your odd man out that would have to be real. So all odd degree polynomials are going to have at least one real 0. All right, but an even degree does not. Another thing is just think about the graph, guys. Any odd degree polynomial, we know the end behavior is opposite, right? So an opposite means it would have to be up on the right and down on the left, or up on the left and down on the right. It has to have opposite end behavior. The only way an odd degree function could end in opposite directions is at least one time it had to cross over the x-axis, right? But an even degree polynomial can end both up or both down. So it might live entirely above the x-axis doing all of its turning and all of its peaks and valleys and never cross over the x-axis because both ends end in the same direction. Same thing. If you are a polynomial function that has to end both down, maybe you're a polynomial function that lives entirely below the x-axis. Maybe you never crossed over the x-axis. Therefore, all of your zeros would be imaginary because imaginary zeros don't make x-intercepts because imaginary numbers don't live on the real x-axis. All right, so that's just something we can go off of. So if you are an odd degree polynomial, you know it has at least one real 0. But an even degree polynomial does not have to have any real zeros, okay? All right, so let's just try a couple problems using these theorems. So this one says, using the conjugate pairs theorem, a polynomial function of degree 5 whose coefficients are real numbers has the zeros 1, 5i, and 1 plus I. Find the remaining 2 zeros. So guys, they told you it's degree 5, which means it has to have 1, 2, 3, 4, 5 zeros. Now again, maybe some of them repeated, some of them could be real, some of them can be imaginary, but I'm telling you, when you count them all up, there will be 5 zeros to a degree 5 polynomial. So they said that 1 is a 0. They said 5i is one of its zeros, and they said 1 plus I is a 0. So they want us to find the remaining 2 zeros because we know there's 2 more left. Well, think about it. 1 is a completely real number. He does not have to have a pair. He could just be 1 as a 0. But 5i is an imaginary 0. So we know his conjugate has to be a 0. So now we know negative 5i would have to also be a 0 to this degree 5 polynomial. Same thing. 1 plus I is an imaginary 0. An imaginary 0 has to come in a pair. So 1 plus I is a 0, then that means his conjugate, 1 minus I, must also be a 0 to this polynomial function. So now they only had to tell us 3, but we were still able to find all 5 remaining zeros just based off of these theorems that we know. Okay? Perfect. Nice and easy. All right, look at the last example. It says finding a polynomial function whose zeros are given. In part A, it says find a polynomial function f of degree 4 whose coefficients are real numbers and that has the zeros 1, 1, and negative 4 plus I. All right. And then in part B, graph it to find graph the function found in part A to verify your result. So guys, we have to write a polynomial function. We have to write the equation of f that's going to be degree 4 and has these 3 as zeros. Well, think about it. If I'm going to write a degree 4 polynomial from scratch, then I need to know all 4 of his zeros. So a degree 4 polynomial is going to have 1, 2, 3, 4 zeros. They told me 1 is 1. They told me 1 is another 1. So he's actually a multiplicity of 2. He's got a double root there. And then they said negative 4 plus I is also a 0. Okay, well, guys, guess what? The fourth zero has to be his conjugate. They have to come in pairs. So -4 minus I has to be that fourth zero. So even though they listed 3 out of the 4 zeros, we automatically knew what that fourth zero was. So that means if these are zeros, then that one theorem said, if you know the zeros, every zero can be written as a linear factor of that polynomial. So we're going to write these zeros as linear factors, and then we're going to multiply them all out, and we'll have a polynomial function who is degree 4 with these 4 zeros. All right, so let's write the polynomial function. Let's write them as factors. So f of x will be a polynomial function. I'm going to put a in front, because we always kind of got into that habit before when we were writing the equation of a polynomial function. Normally, if they're not going to tell you any information other than the zeros, then a is going to be non-distinct, right? We're just creating, in general, a polynomial function that has these 4 zeros. There's lots of polynomial functions out there that could have these 4 zeros. To make it not distinct, I'd have to have more information to go off of, like another point that I could plug into my equation to solve for a more distinct value of a. But I'm going to put it there just out of habit, even though we'll most likely just let it end up equaling 1, because 1's the easiest number to let it be when they don't give me any other information to go off of. But I like to get in the habit of putting it there. All right, so now let's take each zero and let's write it as a factor. So if 1 was a 0, I could write that as a factor of x minus 1, right? Because if I set this factor equal to 0 and solved, I would get x equals 1 as my 0. All right, if 1 is a 0, then I can write him as a linear factor, x minus 1. Okay. Now, these ones get a little bit weirder, right? It's just a habit that I've gotten into doing this, and I find that the students who don't do it tend to get these ones wrong sometimes. All right, but think about it. The reason I write it like this is, yes, I know if -4 was a root, right? I could write that as a factor of x plus 4. Okay. I could also write it, though, if -4 was my 0, I could also write it as x subtract -4, right? And the reason I like to do this for the harder ones, it makes it easier when you go to simplify it. So we don't get, because there's multiple pieces that you have to take into consideration. So there's kind of like a distribution that you have to take into consideration. So even though this doesn't seem right, the way I like it is, though, if you were to set this factor equal to 0, you would still get -4. And the only thing you have to do is I could just add the -4 over, and then he cancels, and I still get x equals 0 plus -4 is -4. But all you technically have to do is add this over, and it gets you your 0. All right? So I'm going to say if -4 plus I is a 0, then I could write that as x minus, this is the weird part, I'm going to put in parentheses -4 plus I. So technically, all I would have to do is add this over, and I would get -4 plus I as the 0, just like it says, okay? And then I'm going to write this one as as my -4 minus I. I'll write that as x subtract, and then -4 minus I. So technically, if I set this factor equal to 0, all I would do is have to add this over, and I would get -4 minus I as my 0, okay? Otherwise, your factors sometimes don't multiply out correctly. All right, now I am going to distribute and get rid of that 0. I'm not going to get rid of that 0. Just get rid of these parentheses here. So now I have a, x minus 1 stays the same, x minus 1, and I'm going to get x plus 4 minus I, and then I'm going to get, distribute this negative, x plus 4, and then plus I. Okay? All right, so guys, you've written them as linear factors. Now it's just your algebra skills. Now they want us to multiply it out. So now we're going to have to multiply and FOIL like crazy, okay? So technically, I'm going to do these ones first. Let me just multiply these together with a quick FOIL. I'm going to get a times x squared. All right, x squared minus x is going to get me -2x's and then plus 1. All right? And then if you want to multiply these out, if I could just suggest something, okay, just to make it quicker and easier. If you think of x plus 4 as like a package, x plus 4, then technically you have x plus 4 minus I, and you have x plus 4 plus I. So if you think of x plus 4 as A minus and I as B, and then you think of x plus 4 as A, and then plus I is B. Guys, A minus B times A plus B, that's how we get the difference of two squares. A plus B times A minus B always multiplies to A squared minus B squared. So now I know that this is going to multiply out to A squared. A was X plus 4. All right, and then minus B, which was I, squared. So you're basically kind of treating it like the difference of two squares, right? So again, x plus 4 is A, and then I is B. So it's A minus B, and then A plus B. A minus B and A plus B always multiply out to A squared minus B squared. I'm telling you, you FOIL A minus B times A plus B, it's A squared minus B squared. So I take A, I square it, and I take B, I square it into the difference of them. And I'm telling you, it does make it easier. All right, so now A x squared minus 2x plus 1, and then times, this is a FOIL in disguise, right? I'm going to write this twice and FOIL it out or shortcut it. First term squared, x squared, 4 times x is 4x, but double it, 8x. Last term squared is 16, okay? So x plus 4, the quantity squared becomes that. And then minus, the second power is I squared. But guys, do you remember who I squared is? I squared is negative 1. So it's minus 1, which is actually plus 1. So that's going to get me A x squared minus 2x plus 1. Oh, I'm off camera. Hold on. All right, and then times, this is going to be x squared plus 8x, and then 16 plus 1 is plus 17. And now all you have to do is kind of do a big FOIL here. All right, so let's distribute. Let's times everything in the first parenthesis with everything over here. So x squared times x squared gets me x to the 4th. All right, x squared times 8x is 8x to the 3rd. All right, x squared times 17 is 17x squared. All right, now we distribute negative 2. Negative 2x times x squared is negative 2x to the 3rd. I'm going to line them up just to make combining easier. All right, negative 2x times positive 8x is going to be negative 16x squared. All right, and then negative 2x times positive 17 is going to be minus 34x, sorry. All right, and then last I'm going to distribute my 1. So 1 times x squared is positive 1x squared. 1 times 8x is going to be positive 8x, and then 1 times 17 is going to be plus 17. All right, so now f of x will equal some a value times x to the 4th. That's going to be what? 6x to the 3rd. That's going to be 1 plus 1 is 2x squared. It's going to be negative 26x and then plus 17. Now, this is what we're talking about. You can be written as non-distinct factors. We're also writing a non-distinct polynomial function that has these 4 zeros. If I knew another point that this polynomial had to pass through, then I could plug it in for x and y and solve for a more distinct value of a. Since I don't know anything else about this polynomial, I could literally let a, that leading coefficient, be anything I want, and it would not affect what the zeros were going to end up being. So the easiest number to let it be is 1. So let a equal 1, and then you don't have to distribute anything in. All right, so if I let a equal 1, then we don't need him in front, and then this just becomes our polynomial function of degree 4 that has these 4 zeros. Now, it said to verify on a graphing calculator. So guys, if I already typed it in, so I took this equation that we just wrote, and I typed it into my graphing calculator, right there, I typed it in. Now if I go to the graph, there is a degree 4 polynomial, right? If both ends are up, and it has a 0 at 1, and it bounces. So that means that 1 was a double root, it had a multiplicity of 2, and the 2 complex, the 2 imaginary zeros, guys, they don't cross over. So it's a degree 4 that only touches the x-axis kind of twice if you think about it, but really it's just at that one point, and the other 2 don't count. So this is definitely a degree 4 polynomial that has that real 0 at 1 and then 2 imaginary zeros where it doesn't actually cross over again. Okay? All right, guys, as always, please reach out to me if you have any questions about any of these notes, and I'd be happy to help. Good luck on your homework, and I'll see you the next day.